bearing with us, Jess.
Oh no, sorry, I was reading the book. It actually does look fairly interesting. And I'm not one for like graph theory. I kind of like during 350, I was kind of just like groaning my head like,
don't be fooled. That's not graph theory.
Yeah, that's what I looked at
what
first.
That
and
is,
I'm like, that's not exactly it.
That's linear algebra.
Yeah.
That's like the next level of. I think of representation theory. To me, representation theory is linear algebra. It's like it's grown up linear algebra.
Yeah, there was a section in the back I didn't notice. It was the item potencies and decomposition, just like we are currently doing.
Yeah, that story plays out again and again.
Yeah.
Yeah. Oh, okay. So I'll begin with the word prayer. Dear Heavenly Father, oh no, here we go. Thank you for this day. We thank you for these students. Just pray that you be with us, help us to glorify you what we do, and just help me to say some useful things today, Lord. In your name I pray. Amen. So guys, I spent an hour or so reading this, Manifolds and Differential Geometry, by Jeffrey Lee. And he has, if you want to read just sort of an introductory whatever on a particular topic you're interested in, it's a great book to look at. So what I was trying to look at was just the problem of what is a fiber bundle, how to construct bundles, and stuff like that. And he has 30 different, it would take me forever, and I get tired, but he has all the basic ideas. And so let me just try to give you the essential idea, and then I'll probably go back to Rentland because he has a pretty, probably not as, Lee will be more general and give you all the different flavor options, let's say. And if you were going to go to grad school and study geometry, you really should read Lee's book and spend some time with it. It's worthwhile. I think both Lee's books. Maybe that's the second one to read. The other Lee's the first one to read. If I recall correctly, I don't think John Lee's book goes that far. This is really just on. Oh no, my laser! Sadness. I forget if this has bundles in it or not. I don't. It might. Oh, it does. Oh man. Oh, this is what I should have read. Curses. Oh well, I can't. What's done has been done. I think I read this last time preparing, and then I forgot that I read it. I'm an idiot. Oh man. Alright, I'm just going to tell you what I know. Curses. So, what is the notion of a fiber bundle? Alright. So the basic idea here of a fiber bundle is the following. You have some space, right? Whatever. And basically all you want to do is just take the space and glue some object on it at each point. Like that. Just glue an object on it. And so you're like, oh. Now if you're so we usually use M as our space. M is the base space, okay? So we're losing our break room, I guess. No.
What are they doing to it?
Man, what are you doing over there? It's not good. Anyway, so you have a base space, right? And I think physically speaking, I think of it as space time or something. That's sort of how I. But that's just an unnecessary physical idea. And then you just think about attaching something at each point in that, right? Now, if you've had Math 200, you already know how to do that. What do? How you just attach? If I want to take a circle, right? And I want to attach a little line segment above it.
Take the Cartesian product.
Yeah, exactly. So this, for example, M would be the circle, and we could let the fiber be unit interval 0 to 1, right? And then M cross F. Well, that would be a way to copy the line segment on each point, right? And for many purposes that suffices, right? But the notion of a fiber bundle is a little bit more twisted, all right? So the thing is, the way that they're glued, let's say, you can envision it's more tricky, right? So for example, the thing people always show you to start with is this Mobius band, right? If I could find it. piece of paper. This probably won't be long enough, but I'll try. So like a piece of paper, right? You just take it. What's that?
Fold it up, yeah.
Yeah, if I fold it. Yeah, if I try to do the whole sheet, it won't work. But if you take this, probably a few times. You take this strip, right? And so, of course, if you think about the bottom half of the strip as being like the circle, right? Just if I just do like this, of course, then I have what I have up there already, the cylinder, right? But if I twist it, let's see here, if I twist it like this, well then it's still, if you think about one of the edges, whichever one, if you think about one of the edges here, right? It's still the case above each point I'm attaching that line segment, right? But the way it's attached globally is not a Cartesian product. It's twisted. It's got some interesting structure to it, right? And that's the sort of thing that a fiber bundle, the construction of a fiber bundle allows for. Now, the fiber here is, I think of as the thing we're attaching. So this I'd usually call E, and that's referred to as the total space, right? In the case of a Cartesian product, the projection, we just do like, you know, P comma F would just be equal to P. I mean, so everything's simple in the case of the Cartesian product, but the more general definition, fiber bundle, or a reasonably general definition, I should say, is given in Rentland here. There's always a way to abstract it a little bit more, or drop a little structure. But so in fact, what I'm going to look here is not even a fiber bundle, but something a little bit more specific. A fiber bundle, you can even let this fiber be like a manifold. You could glue a 3-sphere over each point on a circle or something, you know. That wasn't cool. I felt that.
Where are they?
I think they're in the break room. If they're not doing demolition on the sink, that would be annoying. Anyway, so vector bundle. A vector bundle is a more specific thing. In a vector bundle, what we have is that the fiber is a vector space. So what you're doing, really, in some sense, is just attaching a vector space at each point above your base manifold, right? And so here's the somewhat careful definition. It's a vector bundle. It's a pair. Well, it's not a pair. It's a, what is this? A 4-tuple. E, M, Y, and pi. All right. So M is a manifold, and E is a manifold. Pi is the projection. It's a mapping from E to M, the projection. And it has to have these 3 axioms. So axiom 1, bundle axiom 1, is that all the fibers are isomorphic. So the fiber is, by definition, inverse image of a singleton under pi. All right, so like these are isomorphic to y for each p and m. Just a second, I'm going to see if I can't put a stop to that. Are you guys working on something? Yes. Okay. Well, it's okay. I just if you got something to do, it's all right.
Were we interrupted?
Well, I'm working in here. You hear you.
I'm sorry.
It's okay. Okay. What did I do? I don't know. It's not the break room. It's I forget. There's a wiring closet over there. Anyway. So, first of all, there's a standard fiber. All right. The inverse image above each point in the base manifold is the same. So, like there's a picture you can draw, something like, right? And then here's M down here, let's say. Right, so, you know, if that's P, then I always draw it like, I don't know why I'm drawing this picture, but I'm going to regret it. So this is pi inverse of P, of course, if you'll allow me to skip this curly brackets. And Joe! He's probably mad at me for not having that pizza party. Oh well. Don't worry, I'm getting back to it. So you got this standard vector space over here, Y, right? And there's an isomorphism from this fiber to the standard vector space Y, and you can do that for every point. The dimension of the vector space is called the rank of the bundle. Bundle axiom 2, all right, is that the manifold is locally a product. So for all P in the base space, all right, there exists a neighborhood U containing P. I can't spell containing. And a diffeomorphism such that there's a neighborhood U containing P and a diffeomorphism. Alright, diffeomorphism phi sub U, which is a mapping from the inverse image under pi of the set U to U cross Y, Cartesian product of U and Y. So, if you read a lot of expositions about fiber bundles, one of the things, I mean, everybody says this, everyone should say this, I should say this. Fiber bundle is locally trivial in the sense that you can pick some neighborhood of P, right? And so relative to that neighborhood of P, you got some setup here. I don't know what it looks like exactly. I mean, whatever, I usually think of it as being like a cylinder. But I guess, I mean, this is just a heuristic picture, right? The point is that there is actually a mapping phi U to, literally a cylinder, right? Which is, U cross Y. And this phi is a diffeomorphism. This is called a local trivialization. And of course, phi trivialization. Well, and of course, this is called the local trivializing map. All right. Nothing too surprising there, terminology-wise. And third axiom. B3. Oh man, I didn't take the black when I picked up the green one. All right, third axiom here is that the local trivialization carries fibers to fibers, and its restriction is linear. So, phi U as above carries pi inverse of P to pi 1 inverse of P, all right? Where pi 1 is actually it's the projection I was talking about over there. It's the natural projection on the Cartesian product. It's just like pi 1 of P comma, let's say little y is just equal to P for all pairs P comma Y. Oh, P is a bad letter. No, it is. Well, no, P is not fixed here, fine. For all Py in the Cartesian product of U and Y. So that, first of all, this maps into that. And more than that, though, what's the nature of phi U restricted to the fiber? It has to be a linear map. Sorry. Alright, so this is a vector bundle. Now we looked at one of these last time, like the tangent bundle's the quintessential vector bundle, where the fiber is just the tangent space. And well, local trivializing map would be, goodness, what would that be?
Just the identity via trivialization. I don't know.
Hmm.
Because it's already kind of like a, well, no, maybe not. No.
I don't know, let's think about it for a minute or two.
Well, couldn't you just take the coordinate map using your
See,
dx1, dx2 as a basis?
So E equals Tm, M equals M, and what was it, we had pi of, how did it go, pi of something like P comma V was just equal to P, right?
Right. So it's already like a Cartesian product.
No, it's not though, because remember, Tm is the disjoint union.
Okay.
So it's not a Cartesian product, no.
Well, a disjoint union is constructed using a Cartesian product, though.
But it's not a
Right.
Cartesian product, no. I mean, let's see here. Let me try to. So, what's the inverse image of a? Okay, so we got to pick out what's our standard fiber. What's our y? This is a fixed. I mean, it's a fixed but token vector space in this setup. So I think we can just let y equal to, say, Rn. Be rather concrete about all this. Right? So the local, we're looking for, let's see here, so let U containing P be a what? Let's let it be a chart domain of M, right? So what that means is that, you know, if Q is an element of U, right? And VQ is an element of TQM, right? Then we can of course write VQ is what? VQ is equal to like a sum I equals 1 to n of VQ acting on the coordinate function xi, partial xi, at the point Q, right? So in the chart domain, the coordinate derivations give you a basis to expand any vector at a point like this, right? And then like in this, so then over the chart domain we have the adapted chart domain upstairs, right? Like up in the tangent bundle I have things like, I don't know, like x of what, of excuse me. Well, it's, I mean, okay, so P, I guess I could do Q, because I was trying to let P be fixed, but arbitrary here. So let's say TQ of VQ, that would be a typical point, right, in the tangent bundle. So, yeah, I mean, point-wise it's pairs, right? But I don't know that the global structure of it's a Cartesian product is my point.
Right. I mean, my thought was, couldn't you take your basis of derivations and use the coordinate map to map that to Rn? Or is that essentially what you're doing?
Yeah, I think so. So our I made, sorry. So I was maybe a tilde on this, fine, since it's the adapted coordinate chart, just for the, since you guys are trying to understand the difference. This is the coordinate chart on the tangent bundle, right? So that would be what? It was x of q, right? This is a particular element of, that's in Rn, right? And then we said we would just do what? We would do like VQ of x1 and so forth, right? And that would give me a element of R2n, and that would be how the adapted coordinate chart worked, right? Now what we're trying to do now at the moment, we're trying to find a, what is it, a diffeomorphism from there to there. Let's see here, what, how to say this, so what's pi inverse? I mean, this is a typical element of, I mean, this is in fact a typical, this is right here, right? This is something in pi inverse of u, right? It's in there, right? I mean, do you agree? Because the q is assumed to be in u, and that's all it takes, right? Yeah. And so I need a way to, I need to say what should, I mean, I think it's almost right in front of us. I mean, I don't think there's really much to do here. Phi u of, and you may have already told me what to do, and I just am slow to hear you. So I want something over here, right? Oh, it's got to be, it's got to be u cross y though, right? So I guess what I'll just do is keep the q, right? And just steal these guys, right? That should work as a diffeomorphism. It's at least in the right thing. I mean, it's an element of u cross Rn like we want, right? Making the usual identification of two tuples and n tuples cross n tuples. I guess the question that remains though is does this local trivialization I'm proposing, does it actually bear axiom B3? Is it linear if we restrict it to the fiber? So now what happens if we fix, say, q equals to p? Right? Just if you want, just fix q. Right? If we fix q, it's definitely mapping, so like fix q, right? Let's say fix q equal to p, just so you can see it better. Then we've got what? We got phi u of p vp is equal to p, right? Vp x1, Vp xn, fine, I haven't really done much there. My point though is that this is in fact, yes, an element of what? I mean, this is in fact pi 1 inverse of p, right? It's an element of that because pi 1 inverse of p here, that is just the singleton p crossed Rn, because pi 1 is it just maps. It's the projection onto the first thing in the Cartesian product, right? So that's right. Now the question then is this mapping linear in V? In other words, is the component of a vector related to the components of a sum of two vectors? Well, yeah. Components of a vector are it's a linear relation. So yeah. Of all the times, it's funny. All right. So wait a second. Now, okay. Now, Lee describes this notion of bundle isomorphism or bundle morphism. There's two types, all right? And so, like, if there's a bundle morphism, as Lee describes, of type 2, such that you can make a correspondence between your given bundle and the Cartesian product, then it's said to be a trivial bundle. A trivial bundle is one for which, it's either a Cartesian product or it's vector it's bundle isomorphic to a Cartesian product. Now we've just shown that locally the tangent bundle, right? Locally the tangent bundle can be put in correspondence with just chart domains crossed with Rn, right? But what would it take to have the Tm was globally the Cartesian product? What would we need? Like, in order to say Tm is equal to M cross something, what's required? Or let's say bundle isomorphic to M cross Rn to be using this notion of bundle isomorphism, that you could, that bundle isomorphism basically means you can find a global trivialization, okay? That's what that means. Looks to me like we would need just a coordinate chart. If we had a coordinate chart which covered the whole manifold, then we could do this argument and we would have a global trivialization. So the question of whether or not a bundle, the tangent bundle rather, can be trivialized is very much connected to the question of, does there exist a global coordinate system for your manifold?
Wait, so is that condition also sufficient? Or, I mean, necessary, yeah.
Necessary? I believe so. Let me see here. I believe so. Okay, so I have a little bit more to say here about all this stuff. Okay, so what happens if you have overlapping chart domains, right? So if U and V were overlapping neighborhoods of P, then you'd have, as he points out, phi V composed with phi U inverse mapping from U intersect V, parentheses, Cartesian product with Y, to U intersect V, Cartesian product with Y, all right? And if you, in fact, let's see, he says by virtue of B2, that's a V. Here's what he says. He says, okay, so what would we get by axiom B2 if we feed this a pair? He says feed it P comma Y U. Now, I think his YU is actually a vector field. He's gradier here. Well, he's sneaky sometimes, you know. You guys remember reading Rentland? Mm-hmm. There are places where it seems like he gets awful far very fast, you know. You gotta watch him, he's a slippery one sometimes. But this would be what? Looking at B2. So this would, let's see, phi, it's a diffeomorphism, right? So this is an invertible map by assumption. So we would go, I mean, that makes sense to feed it a pair in here, right? Then the inverse image under phi U goes back over here, but then phi V takes it back over here. Okay. But I guess the point is when it comes back, it's... Oh, it's just notation he's using. I got it. It would be PYV is what he's just using this as a notation. Okay, and if P is fixed, how are these related? He says YV is equal to GVU at the point P, YU. And what's the, here this GU, just GVU P is a non-degenerate endomorphism of the vector space. It's, in other words, it's a linear transformation from Y to Y, which is invertible. All right. Let me just walk us through this again. So because it's a diffeomorphism, you can compose it, right? You can compose it to go to and from this space by going first to the one trivialization and then back again. Then if you freeze P, you have to have by axiom 3 a linear thing, right? And it has to be that the restriction is also injective, because you can't restrict in diffeomorphism injective, right? You can't restrict diffeomorphism and get something that's degenerate. That'd be crazy. So it must be that this, when you freeze P, is a non-degenerate mapping from Y to Y. Therefore, there must exist something in, let's say, this would be, we would sometimes use the notation GVUP is what? An element of GL, GLY. It's something in the invertible linear transformations from Y to Y. All right? So there has to be this, if you look at this sort of composition of these local trivializing maps, it has to basically produce for you, you know, if I rewrote this again, it would be what? P comma G VU, right? Of PYU, right? So you could see, in other words, this composition of these local trivializations is completely captured by multiplication by this invertible linear map. So there's an intricate, intimate connection here between the composition of these things and simple multiplication by these very particular kinds of invertible linear maps that are connected to the structure of the bundle. In fact, these endomorphisms are called the bundle transition functions. And if you sort through, what would be, if you think about what this means, if you go, say, run this bit of logic on, local trivialization composed with itself, all right, and then think about the fact that you can either go like U to V or V to U, right? And what else can you? And then you could also use, like, if you had triple overlap, you could look at the transitive, look at the transitive conditions. Anyway, after the dust settles, you get these Cocycle conditions on the bundle transition. The Cocycle conditions on these G's, in particular, GUU at P is equal to the identity. GUV at P times GVU at P is what? And finally GUV, GVW, and GWU, all at the point P. So the last three also identity. These are the Cocycle conditions. And all right. I think if I remember from Lee's book correctly, he also calls the local trivialization, he calls it a bundle chart. A collection of bundle charts where the union of the U's covers M. So if like the union of the U, the sets of U, if those cover M, then like a collection of bundle charts gives you a bundle atlas. Something like that. So a trivial bundle permits a bundle atlas which just has one global chart. It's globally trivial, and the Cocycle conditions are very silly. There's just the identity. All right. That's it. Exercise 7.1 on page 178 of Rentland. Would you like to do it? I think I just walked you through it, though. It's basically just applying these axioms to this observation. Now, a smooth section. What's a smooth section? What's a section of a vector bundle? A smooth section, if you have a mapping S, all right, from the manifold, the base space, right, up to the total space E, such that what we need is the projection of the vector bundle composed with S is equal to the identity map. This is called a section. You can also talk about local sections. What's a local section?
Just the same thing in some neighborhood of M.
Right. It's a local section would be something like S from say U, to E, such that what? Pi composed with S is equal to the identity on U. Now, as he says, as we were talking about already, he says, useful to have a criterion for triviality. That's provided by the next result. A basis of sections, all right, what's a basis of sections over a subset U? Is a collection of n sections that is linearly independent at each point of U. Such a smooth basis of sections is what we would have called a frame field, right? All right. He says, as E is locally a product, we can always find a basis of sections for any sufficiently small neighborhood of M. But what about larger neighborhoods? And here's his theorem. So let me just go through that again. What did I just say? Definition basis of sections. What is it? Basis of sections is just what it sounds like. Basis of sections on U would be, so he hasn't defined, I don't think he's defined local section, but now he's using the concept. That's fine. That's what makes this book easy to read and yet hard to read. The basis of sections on U is what? Is local sections, right? E1 en, all right, such that he says linear. What does he mean by linear independence of those? Ooh, it made sense when I said it, but now that I think about it, I gotta think about it.
Like the vector spaces it maps to.
Right.
Like what he was saying about the frame field.
So he wants to say that E1 of P, E2 of P, and so forth, right? En of P is linearly independent at each P in U, right? But the thing is, Those are points in the total space, right?
So E1, the E's, are they points or what are they again?
Well, okay, so like here's the total space, right? Up here E, right? And then down here is M, right? Here's a point P. And so this, all of these points, I mean, there's like n of them, right? Like E1 of P, E2 of P, En of P. They're up here because the section goes like this, right? Well, in this case, I mean, there's a bunch of them. Right, the sections go from the base space up to the total space.
Yeah.
And I do know that, I mean, I know that I know pi of EIP is equal to what? Equal to the identity of P, which is just P, right? For all I equals to 1, 2, da da da, n. So I do know that they're in the fiber over P. How do you judge, what does it mean that they're linearly independent? That's not a vector space. It's a particular...
It's not locally isomorphic to vector space, though.
Exactly. It's locally isomorphic. So the point is, I can't judge linear independence there, but what I can do is judge linear independence. Like over there. I can use the local trivialization, right? So something like that, I think. So if we pick what's meant when I say that that's linearly independent is that its image over in the local trivialization is linearly independent. And actually, so you have like, you know, phi, let me just call it, be really dangerous, let me call it phi sub p. Oh. U tilde, fine. This is a mapping from I'll get over it in a second here. Pi inverse of u to pi inverse of u tilde to u tilde cross y, right? And that should be a that should be the local diffeomorphism, right? And so to say that basis of local sections is linear independence, what that really means, right, is that if you feed it to the local diffeomorph, but that, even here, it's not quite what I want yet to judge linear independence. What do I need to do? It's really saying...
Second element, the
Yeah.
projection.
Right, so what I want is something like phi u tilde, sorry, still wrong. Something like pi 2 of the local trivialization, phi u tilde, of E, I, P, I equals 1 to n is linearly independent in Y.
That's actually what I wanted to say, but I was hesitant to use type theory notation. That's the map they use in type theory for the projection of the product.
Oh, okay. Yeah, I
mean, I think it's pretty standard. But
right, yeah, the second, if there's two things, it's the
Yeah.
second projection. This was the first projection over here. Yeah. That's what it has to mean. Yeah, so... Right. Okay. Now, so we can always get a basis of local sections, right? There always exists a basis of local sections in a vector bundle because you can do what? You can use the coordinate derivation. Well, I'm sorry, maybe I can't. I'm thinking tangent bundle. Sorry, I'm thinking tangent bundle. Certainly in the tangent bundle, we can always get a basis of local sections by using the, building it from the coordinate derivations, if nothing else. I must say that, sorry.
Could you use P sub U inverse?
Where, which one? What do you say? Phi?
Use the inverse of the diffeomorphism to get a basis in the vector space.
So you're saying go backwards.
Yeah.
To pick a basis in Y and just pull it back, basically, like use
Right.
the inverse map to transport it over to something which is fiber-wise going to map back to a basis by its construction, and that will give you a local basis. Yeah, I think that's right. Yeah, very good, very good. And that doesn't, that notion is not restricted to the tangent bundle. That's a vector, that's a fiber bundle comment you just made. That's a good one. Very good. Yeah, so when you're studying vector bundles or fiber bundles, you give a lot of competing notions of how to characterize. It's like local behavior. You can either look at things through the lens of these local trivializations, or you can look at things through the lens of local sections. Both of these are useful for proving properties of fiber bundles. I've started from the top down. Like, here's a manifold, here's another manifold, here's a projection. It locally looks like this. That's how you construct it. We derived Cocycle conditions. There's another way of doing things. In fact, you can prove that if you have a set of these functions, these cocycles that satisfy the Cocycle conditions, you can use those to build a bundle. If you have the devil's in the detail of the P over there, like you have more than one cocycle for the P varying over the base space. Like, given a base base manifold M and cocycles that satisfy the Cocycle conditions and the relevant smoothness conditions, you can glue basically together a bundle which reproduces those Cocycle conditions in this way. This is a well established procedure of producing bundles. You can do that.
So the G sub VUs, those are the cocycles?
Yes, yes. And again, this is just vector bundles we're talking about right now. There's something else called a principal bundle. A principal fiber bundle. The fiber is not a vector space, but it's a group, a Lie group. And so, like, every fiber is a Lie group, and it turns out that the structure, that the analog of the G's in that context are the Lie group again. So, like, for a principal bundle, the fibers are also these, and these are the fibers, and principal bundles are interesting. Probably the most interesting principal bundle is called the frame bundle. The frame bundle has base space, the manifold, and then over each point you attach all possible frames, where frames are excuse me. We could just say basis for the tangent space, all right? So if you think about a basis for a tangent space, it's a set of n linearly independent vectors. If you glue those together, what do you got? Well, you've got an n by n invertible matrix. So if you can think about taking the base space and gluing an n by n invertible matrix over at each point in a smooth fashion, that gives you the frame bundle. You can use the frame bundle in something called the associated bundle technique to produce tangent bundle, cotangent bundle, and like other things that have like differential form bundles. And I mean, any of the objects that we've talked about in advanced calculus, you can sort of globalize them through looking at an associated bundle attached to the frame bundle. It's a well-established technique that I was hoping to tell you about, but Lee has reminded me how many details that there are to share. So I'll just leave you the idea at the moment. Alright, so big idea here. If there's something more than just trivial, right? Now I've told you about if there's a global coordinate system, we could find a global trivialization, right? And that would be hand in hand with the fact that, just like I said, you can write it as a Cartesian product of M cross, well, I guess Rn, basically, it's that, right? But there's another way you can talk about it, which is parallelizability. Tm is trivial, then M is called parallelizable. And that has with it a more geometric notion, which he hasn't explained yet here, but what's parallelizable mean? Well, I mean, he's basically saying, definition, if this happens, M is parallelizable. Now, as we study manifold theory more here, this with our time remaining, what I'll try to show you guys is parallelizable just means that there's a notion of parallel transport. Like you can, well, that's not quite it either, is it? I mean, that's, yeah, I guess that would be one way you could maybe, a rather clumsy way of characterizing it is, there's a notion of parallel transport, and it doesn't matter what path you take. If you take two vectors and you like, so you know, on the sphere, right? If you take a vector, right, and you do what's called parallel transport it from like here to here, it might go one way, right? But if you did the same process of parallel transporting the other way, and I can't draw it with anything, you'd get something else. And so parallel transport along two different paths, whatever this parallel transport means, I've not defined that for you yet. I'm just saying it's something you can do. We do it all the time in physics. Look, I attach the point vector here, and then I keep its orientation the same, and I'm parallel transporting it, right? So we know what it is in Euclidean space, but how do you define that over a curved space? Right, that's a question. How do you carefully define this notion of parallel transport of a vector over a curved space? Once that's settled, though,
so why does that change the orientation, though?
Well, that's the thing, is the details of the parallel transport, if I had half a brain and I could remember it, I could explain to you geometrically right now, but
yeah.
I don't, so I can't. But the bottom line is, once we describe it, you would get different vectors over transporting, starting with the same vector, going different paths, get different end points. If the space is parallelizable, there's some parallel transport which doesn't matter which path you take between 2 points, you produce the same vector afterwards. Mm-hmm. Like the case is for Euclidean space, right?
Yeah.
Like Rn, it doesn't matter if I parallel transport this vector from here to here. It doesn't matter if I start like this and go. When I get over here, it's still that, Yeah. As opposed to if I just go like that. As long as my transport is parallel, I end up with the same vector. Because Euclidean space is boring. But for curved spaces, there's some interplay between the geometry, the topology, or I don't know about topology, but the the shape of the space and the transport of the vector. And that's tied to this question of whether or not the tangent bundle is trivial.
Is S1 parallelizable?
I think S1, S3, and S7 are parallelizable. That is, and that's part of a more general theorem. A Lie group, if G is both a manifold and an abstract group, right? So G is a Lie group. What is that? A Lie group is a manifold with smooth group structure. Okay. That was structure. Sorry. Anyway, a Lie group can be shown to be parallelizable. You have this left multiplication in the group, like you can multiply. Basically, that gives you away from getting to the identity to any point in a really nice way, this left multiplication. And so you can show that a Lie group is parallelizable. I mean, you can show that the tangent bundle to a Lie group is isomorphic, diffeomorphic to the Lie group cross Rn, where Rn is the dimension of the Lie group as a manifold. Getting back to Nathan's question, S1, S3, and S7 permit group structures which are smooth. S1, the circle, is essentially the unit complex numbers. S3, well, that's the quaternions, the unit quaternions, those form a group. In fact, a Lie group. And S7's the unit, I believe it's the unit octonions, which also, despite their lack of associativity somehow, how does that go? I don't know, but S7 somehow permits a group structure. Don't ask me about that one. I'm not sure about that one. I'm less familiar with that. I know it's true, but yeah. So yeah, but other spheres, like the 2-sphere, or the 4-sphere, or any other spheres, those are not parallelizable.
Yeah.
And the other way to think about this is, what does it mean to have a global section of the tangent bundle? What is that? What you're doing is for each point over the base space, right? You're picking one point in the fiber, right? What does that mean? I mean, right? Well, that's a bad picture. Base space. Okay. Let's stick with I don't need to make it 2-dimensional base. Let's think about the base space as a 1-dimensional thing. So at each point in the base space, right, you're picking a point up here, right? This is, S, a section, right? Of course, this point is in 1-to-1 correspondence with a vector, where a vector here. This is a vector field. So the existence of a global section for the tangent bundle is exactly the same thing as saying there exists a vector field, right? A vector field on the tangent bundle. I mean, a vector field on the manifold, which is defined over the whole thing. And I should be more careful. The fact that that is, you could do that. You can do that over any manifold. Here, let me define for you a global vector field on any manifold. The value of the vector at an arbitrary point shall be 0. That's smooth, but stupid, right? We're talking about globally non-trivial vector fields. That's the thing. That's the theorem. There does not exist a globally non-zero vector field on the 2-sphere because the 2-sphere is not parallelizable. That's not an easy thing to prove. That's a deep theorem I'm quoting. Okay. It's connected to a larger circle of ideas, the Gauss-Bonnet theorem and things I talked about with Daniel last summer that would take us some time to develop.
What is the Gauss-Bonnet theorem, briefly?
Oh, well, briefly, since you asked.
Oops, guess I shouldn't have. You have a visitor.
I do. But is it a valid one? Oh. Yeah, okay, well, my grader's gone already.
Does homework 9.
Yeah, okay, thank you.
Okay, thank
Alright. Yay. He is chronically late. Oh well. It's okay, I'm gonna fix them. Next semester I'm not collecting homework. Problem solved.
Doing Dr. Strano on the homework.
Is that what he does? He doesn't collect
Well,
homework?
he
either?
collects it, but he doesn't grade it.
Yeah.
He gives everyone a 90
Oh.
for homework grade.
Really?
Well,
Wow.
At least that's what I never paid attention to like the final grade, but that's what I heard. And we never got our homework back.
Strange.
He gives solutions to it, but
One of
you
the-
kind of forgot what you put for it. But
Yeah, you can't argue it.
yeah.
Can't argue it if you don't remember what you put.
So does this existence of non-trivial global vector fields on a manifold relate to differential equations, like what were we talking about towards the end of last semester?
I'm sure it does, but I don't know. I can't explain that quickly. I don't know. I mean, there's that. What's it called? Oh, the Poincare-Hopf index theorem. Let M be a compact manifold without boundary. X a vector field on M with only isolated zeros. Then the index of X at P is equal to the Euler characteristic of M. Sum of the index of X at P. For P ranges over all the zeros of X, and chi of M is the Euler characteristic of M. I seem to have opened a can of worms. I'd like to close it just now. I will answer your question though. The Gauss-Bonnet theorem says this. It says that the integral over a manifold, this has to be a compact